Hello everyone and welcome to today's webinar on the green hydrogen work DNV have produced for the EI. My name is Amy and I'll do a brief introduction to this webinar and also moderate the Q&A session later. So before we begin, just the webinar housekeeping. As you can see on screen, the webinar is being recorded and will be made available on YouTube in due course. All participants are muted, but we do want this to be an interactive session, so please feel free to post questions in the Q&A function and they'll be answered at the end. So I'm now going to just quickly introduce the EI for those who haven't heard or worked with us before. The Energy Institute is a professional body for the global energy industry, delivering good practice, knowledge and training across a wide range of topics and through a wide range of resources, including good practice, events and training. And to find out more, please visit the EI website. And if you're not a member already, please feel free to check out the EI website again and see what we have to offer. As I'm sure whoever you are, whatever job or role you do, we have something that is applicable to you. So the Technical and Innovation Programme produces good practice guidance, and this is developed via committees made up of subject matter specialists. There are 30 plus projects commissioned each year and hundreds of published documents on the EI publication site. The topics vary from aviation to environment, as well as others that you can see on screen. And if you're interested, please visit this website. So part of the EI is the EI Academy, which offers expert-led training courses. And the EI has a growing portfolio of training courses in hydrogen. Two notable courses to mention are our hydrogen-based energy system courses. Both are self-paced online courses that you can complete in your own time, wherever you are based in the world. Please do get in touch if you'd like to discuss training more with webtraining@energyint.org, and there's also this link down here. And then finally, we have an Executive Leadership in Energy program, which is a 10-day program designed to develop strong future leaders who will be instrumental to the success of the energy transition. And now, without any further ado, I'm going to stop talking and I'm going to hand over to DNV to commence today's webinar. So I'll stop sharing my screen now.
Okay, great. Thanks so much for the introduction. So I think Finlay is going to share the screen from DNV side. So brief introduction to the faces you can see on the screen now to start with, and then we'll get on with things. So my name is Richard Cartwright. I'm a senior consultant. I've been at DNV for about 2 years now, working in the Energy Strategy Advisory team in the UK with a focus on hydrogen specifically. Before joining DNV, I worked as a scientist and R&D manager at a hydrogen fuel cell manufacturer. So I'll pass on to Gwen now to introduce herself.
Hi there, I'm Gwen Jackson-Johns. I'm a senior consultant in DNV's Energy Strategy Advisory team. I've got a background in chemical and energy engineering, and I support the development of this guidance document we're discussing today. I'll hand over to Finlay.
Yep, Finlay, also a senior consultant with DNV, been here around 5 years. Background is chemical and process engineering.
Cool, thanks guys. So what we'll do today is we'll go over a few sort of, so I'll give a quick introduction to the document and to DNV, and then I'll pass on to Gwen and Finlay to talk about some of the more detailed aspects. So they'll discuss what green hydrogen is, how it's defined, how it's made, and key design, safety, and operational principles of green hydrogen production facilities. And then we'll finish with a few minutes of Q&A at the end, hopefully. Next slide, please, Finlay. So DNV is a big company, so it's a global assurance and risk management company. It's headquartered in Norway. It's got a fairly major worldwide presence. It started out 160 years ago as a shipping classification society, but in recent times it's become more interested in other aspects. These include things like energy, software, digital solutions, and supply chain and project assurance. Next slide, please, Finlay. So DNV as a whole has spent a lot of time in the last few years working on all aspects of the hydrogen economy. So we've seen hydrogen projects at all stage development with experience from concept design all the way through to support during commissioning and operation. We've therefore seen some of the key issues that arise during project development and how they are managed and solved by the teams involved. Alongside this, we also perform a lot of strategic and techno-economic work for various clients, including governments, regulators, and as well as safety and compliance and due diligence services for various OEMs, developers and investors. Next slide, please, Finlay. So we've used the expertise that we've got in our team and also in DNV as a wider entity to develop over 6 months during 2023 a guidance document for green hydrogen production. This was done on behalf of and in collaboration with the Energy Institute's Power Systems Committee. The main aim of the document is designed to give clear and practical guidance to industry on the key aspects of green hydrogen production, and it should be available from April this year. The study includes quite a few things, and we'll focus on a few of them in more detail during the course of the discussion today. But it includes things like design considerations, electrolyzer types, operation and maintenance considerations, and things surrounding co-location. So that's either you locate it with a renewable power source or with a hydrogen consumer. And the document also discusses the regulatory landscape for green hydrogen and how government support is developing for the industry as a whole. With that, I'll pass on to Gwen to discuss current definitions for green hydrogen.
Yeah, okay. So green hydrogen definitions, if you go on to the next slide, thank you. So green hydrogen broadly refers to hydrogen produced from renewable energy sources, and it represents a rapidly expanding market. And this brings a diversity of technologies and ultimately a greater divergence into what can be considered green. And so it's therefore important to establish common principles around low carbon hydrogen to provide greater confidence and transparency. So I'll first run through some of these key definitions. So schemes are specific standards or a piece of legislation that define green hydrogen. International schemes have been launched which recognise the need and have developed guidelines for the use across hydrogen supply chains. The system boundary is a crucial and in the definition of green hydrogen, as it marks the boundary for green hydrogen schemes. There are two main system boundaries employed in green hydrogen schemes, and the first is commonly referred to as well to gate, which extends from the electricity generation to the point of production. The second is well to wheel, which extends from the electricity generation to the point of use. So the tracking model underpins the system boundary, and it's used to trace the chain of custody of hydrogen. So two approaches can be taken here, either a mass balancing approach or a book and claim approach. So the mass balancing involves the total mass of the chemical reactants being correlated with the total mass of the products. So this approach links the certification process with the physical delivery of the hydrogen at each stage of the delivery. And for the book and claim, the physical delivery of the energy carrier and the issuance of the certificates are not linked to each other. So the certificates are representative of a determinable quantity of hydrogen at the point of production, but it doesn't involve the physical trading of hydrogen. And lastly, the renewability requirements. So renewability requirements are used to determine the credentials of green hydrogen. Most schemes consider the renewability of electricity generated prior to the hydrogen production, and some require geographical or temporal correlation of the electricity generation relative to the produced hydrogen. Some schemes also consider whether the electricity consumed in the hydrogen production process is believed to be additional, and this is called additionality. And it loosely refers to the principle of which green hydrogen is produced using new renewable energy capacity, although there's some variations between the schemes. And so there's other requirements as well, not encapsulated in the distinctions above, but this might include the encouragement of wider social benefits and other considerations such as water use and land use. Okay, next slide, please. So in RED 2, the requirement are either direct connection to the renewable power with an additionality requirement. And this additionality requirement is that the renewable electricity plant must have been put into operation no earlier than 36 months before the electrolyzer. Or if it's grid connected, there are two approaches. So these are the ones on the right of the slide. So the first one is that the electrolyzer must be in the bidding zone with 90% renewables in the previous year. And this essentially ensures that the electrolyzer is drawing power from the green grid. And the other approach is that additionality, temporal and geographical correlations are required. So as I mentioned, to meet additionality criteria, the renewable electricity plant must have been put into operation no earlier than 36 months before the electrolyzer. To meet the temporal correlation, the generation should take place within the same month, However, from 2030, the idea would be that this would move from hydrogen being generated within the same hour as the renewable electricity. So to meet the geographical requirements, this is that the renewable electricity plant and the electrolyser must be located in the same or an adjacent bidding zone. And the bidding zone is the largest geographical area within which market participants are able to exchange energy without capacity allocation. So next slide, please. So where is this heading? So in the future, it'll be less about the hydrogen and more about the origin, as grid-connected hydrogen production means it's quite difficult to guarantee renewable hydrogen status. So this idea of a product passport comes up in the IEA's publication, which was released last year, and it's called the Towards Hydrogen Definition based on the emissions intensity. It's in its infancy, but the idea comes from considering how developers could be helped to assess different markets while considering needs to meet their regulatory requirements as well. So the product passport can standardise the process and increase the efficiency and transparency of green hydrogen production. Next slide, please. I think I'll hand over to Finlay.
Back over to me. So Gwen has defined green hydrogen, but how do we actually produce it? Well, the first means to discuss is biomass gasification. It's a very well understood, mature process now, albeit complex, but it's essentially the thermochemical breakdown of carbonaceous materials into syngas, which is carbon monoxide, carbon dioxide, and hydrogen predominantly. Four-part process, generally speaking. Pre-processing involves drying the biomass and macerating it down to the right particle size. Then we have gasification. We take lots of heat and make endothermic reactions to release the gas. We then have to clean that gas up, give it a good scrub, and then we separate the hydrogen out using pressure swing adsorption, also known as PSA, or membrane tech. One other means, which is a bit more in vogue at the moment, especially in the UK, if you've been listening to anything on the hydrogen allocation rounds or the global scaling up of hydrogen production for energy transition, is water electrolysis. Simple process, really. Take electricity, split water into hydrogen and oxygen. And there's predominantly 4 chemical reaction pathways available for conducting water electrolysis. Going from order of least technically mature to the highest, we have anion exchange membranes, AEM, solid oxide, SOEC, proton exchange membranes, PEM, and alkaline. And for the rest of this presentation, we'll be predominantly focusing on alkaline and PEM, given that they are the most commercially mature and given that they have commercial operations in practice right now. So perhaps to start with PEM then, and a quick chemistry lesson. You can see a PEM cell here in the top left. It has an ionically conductive solid polymer electrolyte between 2 electrodes. And when voltage is applied between the 2 electrodes, the negatively charged oxygen in the water loses an electron. This results in positive hydrogen ions, which then travel through the proton conducting polymer towards the cathode, where they then take an electron and form hydrogen. I won't go through the typical system layout of the time constraints, but some quick pros and cons. It's a mature technology. There's pilot plants already in operation at around 20 to 30 megawatts around the globe. It's a compact system, which particularly lends itself well if you were thinking of a site that had like footprint constraints. And then it has crucially high dynamic capabilities. Why is that important? Well, it essentially means that it can cope well with ramping up and down with variable loads. So it can really go from 0 to 50, 50 to 100% very quickly with a fast response. And with all the renewable energy sources that are going to be built out over the next 30 years, it's something that can hopefully tap into. Some cons, well, it's currently more expensive when compared to alkaline. I think 20 to 30% capex up front is usually a good ballpark number. Longevity, it's not as well proven. It's not there's not as many of them in operation for us to take data from to adequately assess sort of cell stack life. And it uses a lot of platinum, precious metals. So then to finish with alkaline, we won't go into much chemistry, but what I will say is that it is a water electrolyte solution, predominantly potassium hydroxide, and instead of a positive hydrogen ion traveling through, in this case it's a negative hydroxide ion that travels through the diaphragm and forms at the anode water and oxygen. Pros and cons, it's the most developed, it's got a global track record as it stands, and it's used across a good variety of industry and end sector uses. And yeah, as we said earlier, vice versa, generally lower cost than PEM. There's 3 bullet points on cons, but they essentially boil down to it's less dynamic. It's not as fast as responding. So if you had it in a direct connection model to renewable electricity, it probably wouldn't respond as well. However, if you gave it a constant base load and it had a constant utilization, it performed very well. Passing back to you, Gwen.
Okay. So I'm going to run through some design considerations here. So next slide, please, Finlay. So the electrolyzer design need to consider 3 main aspects, and these are efficiency, durability, and cost. So the aspects are related to each other. However, improving one of these can lead to a detrimental effect on the other. So for example, a thinner membrane results in an improved efficiency, but the durability decreases. A thicker membrane is mechanically stronger and leads to longer lifetime profiles, but it also increases the resistance to transport of charges, which in turn decreases the efficiency. So while the longer lifetime results in lower cost contribution of the investment component, the lower efficiency results in higher operating cost, given the higher electricity consumption. So next page, please. So these are the main topics that are covered in the report. So I'm just going to go and expand on each of them in the next couple of slides. So a stack comprises of multiple cells, and a large plate is placed at each end to apply a current and compress the stack to ensure that it's sealed. The level of compression used for the stack is key to ensure that the seals between the plates are reliable. The membrane or diaphragm separates the hydrogen and oxygen. However, gas crossover can occur via diffusion in both PEM and alkaline systems, or in advection in alkaline systems. And advection is when the liquid slushes back and forth through the separator. The gas crossover is the contamination of the hydrogen gas side with oxygen, or vice versa. And there's a balance between the maximum allowable gas crossover and the minimum separator required. So as I mentioned, a thinner separator allows for high efficiency, but it risks a higher gas crossover rate. When bubbles form on the surface of electrodes, their efficiency sort of decreases as the surface area is reduced. So it can cause fluctuations in current density and the rate of reaction. The bubbles are removed as they tend to accumulate on the most active sites, and this is removed with large volumes of water typically. Next slide, please. So a wide load range is desirable for electrolyzers, receiving seasonal and daily variability, as Finlay's mentioned already. So changes to loads impact the electrolyzer temperature and pressure conditions. And if you operate outside of these conditions, it'll ultimately impact the efficiency. So electrolyzers with a greater tolerance are more suited to hydrogen systems, powered hydrogen systems, sorry. The real world impact of variable renewable electricity is not really understood, as there's not data from OEMs available at the moment due to the lack of commercial electrolyzers. But in general, there's a few ways that the intermittency can be handled, such as introducing batteries or combining renewable energy types to ensure a smoother profile of renewable source. And overloading means that you run the electrolyzer at a higher current density than the rated capacity. This is typically up to 120% of the rated power. So currently only PEM electrolyzers can operate under these conditions for short periods of time. However, OEMs are looking to improve this for both alkaline to be able to go up to 300%. The full impact on the electrolyzer is unclear, although it is likely that it will impact the efficiency due to the additional stress on the materials. So looking at the lifetime, The electrolyzer lifetime is typically affected by the aspects that I've mentioned previously, so gas permeation, variable loads, and overloading. But also water purity is something to consider. So when you circulate low water quality, it can lead to the degradation of the diaphragm and other components. Typically, an alkaline electrolyzer can take lower water quality, but PEM electrolyzers are very sensitive. So we've got references for around 80,000 hours for alkaline and 70,000 hours for PEM electrolyzers. Next slide, please. And back to Finlay.
Yeah, so implementing safe practices. Now, safety, especially around hydrogen production, storage, transport, end use, is its own webinar and seminar in itself. So just going to give some high level considerations over the next 3 slides. So we've split it into plant level and electrolyzer component level. So some examples at plant level: hydrogen releases from pipework, release of potassium hydroxide if it was an alkaline electrolyzer, electrolyzer waste streams of dissolved gases. We've got more detailed example coming up on that. Oxygen stream outlet. And for the electrolyzer component level, we have H2O2 gas crossover. Gwen's already described that. And electrical discharge. So some more flavour on the waste streams of dissolved gases. So electrolyzers can generate aqueous waste streams. These often have hydrogen and oxygen dissolved in the waste stream. And these waste streams include water condensed and periodically drained from wet waste gas vent systems, water periodically drained from product gas dryers, and water or electrolyte drained from systems during maintenance. So naturally, as these streams leave the systems, what we want to watch out for is these dissolved gases evaporating from the solution, and to make sure that if they do, or when they do, especially if it was into an enclosed space, that it's well ventilated to ensure adequate dilution, to keep it below the LFL of hydrogen, which is around 4%, I think. Best practices around this: well, using an open drain that allows degassing into a well ventilated space away from any ignition sources, and using dedicated drains to avoid connecting to other water drains where escaping hydrogen could accumulate or migrate to any unintended areas. And an example then on H2O2 gas crossover. So Gwen lightly touched on it, but essentially what it is gas crossover is when either oxygen or hydrogen remains dissolved in an alkaline electrolyzer, dissolved in the electrolyte, and it forms at the wrong electrode. And it could present obviously an explosion risk, especially when we take into account hydrogen's very low flammability and its ignition limits. However, it does typically occur, but it just does so at a very low concentration, typically parts per million or lower. However, during transitional process conditions, it can accumulate much faster. So, for example, during startup or as cell stack pressure creates an imbalance. But currently in industry, there's already some pretty good barriers in place to prevent this. So, in commercial operation, if crossover is typically limited to 1.8 to 2% hydrogen at the oxygen side, above which it's detected and an automatic shutdown occurs. And other safeguards might include improved design of diaphragms and membranes to increase their durability, and an additional catalyst to convert the permeated hydrogen back to water on the oxygen side. Back to you, Gwen.
Thank you. Next slide, please. So I'm going to be discussing a bit about operating models. So looking at how external influences can impact on the model's effectiveness. So here we'll start looking at the operating states of an electrolyzer, as these are directly impacted by the operating model. The electrolyzer operation is not instantaneous, and therefore an electrolyzer operates under different states. And these are production, standby, and IDAR. In production state, the efficiency is near constant. However, degradation of the stack causes the efficiency to decrease over time. Stacks need to be replaced when the efficiency value falls below 90% of its initial value, and this may occur several times over the course of the plant life. In standby, there is no hydrogen production. However, to maintain the sustainable pressure and temperature, electricity supply is required. And then the last one is idle state, and this is where the electrolyzer is cold and depressurized, essentially turned off. Next slide. So during the operation of an electrolyzer, the transitioning between different states is required. So if we look at transition 1, standby to production, this is also known as a hot start, typically takes place within a few seconds. For PEM electrolyzers, it takes around 5 seconds, and for an alkaline, it's slightly slower, taking up to 30 seconds. Transition 2 is a cold start, going from idle to production state. And these are typically advised against by manufacturers, with kind of a quote of up to 5,000 cold starts during a system's lifetime recommended, and no more than that. And it typically takes 5 to 20 minutes to go from idle to production state. Transition 3 is, transition 3 and 4 are both kind of production to standby and production to idle. And these are kind of considered instantaneous. And then transition 5 is idle to standby and standby to idle. And this is not recommended, only transition from production to idle and vice versa. So moving on to some examples then. The report discusses 4 different models. So 2 of them prioritize hydrogen production, and the other 2 kind of focus more on the use of variable renewable energy and use hydrogen electrolysis as sort of a means for flexible generation. So next slide, please. So the first one is a direct connection to an electrolyzer from renewable energy. So this model is directly connected, and due to the nature of the renewable energy, there's variations in the energy supply that the technology receives. So this would require an electrolyzer that is capable of handling these sorts of power variations. So this would currently be pressurized alkaline or PEM electrolyzers. And without a battery or a generator, the system would only be capable of the cold starts, as I previously mentioned, and these aren't typically advised. So there's a balance between the cost of a battery and the extent of degradation that the electrolyzer will encounter from cold starts. So these things need to be weighed up. So this model also requires the connected systems to respond to load changes in the same rate. So in addition, in times of low generation, the connected systems should also be capable of operating at a lower power. And when you're considering larger scales, like for example, if you're feeding the hydrogen produced into a hydrogen network, the variation in hydrogen supply is less problematic. Larger wind farms will have more inertia, and then as a result, less fluctuations compared to smaller scale. Next one, please. So this model is kind of assumes a power purchase agreement. So a power purchase agreement is a contract between energy buyers and sellers, and the power associated with a PPA is transferred through a power grid as any other power would be, and this provides a steady electricity supply. PPAs allow green hydrogen producers to engage in contracts with renewable energy producers to ensure that hydrogen production will incur constant and forecastable costs compared to variable renewable energy costs. And this model is likely to suit on-demand consumers, such as hydrogen refueling stations. A steady electricity supply means there's less restriction on the chosen electrolyzer type, as there's no restriction on the operating range, and hot starts are enabled with a grid connection, and this is critical if you're wanting to meet the variable demand. Next one, please. So the third model looks at a demand-side response. So renewable energy is prioritized here for the electricity grid rather than hydrogen production, and only surplus renewable energy is supplied to the hydrogen production plant, so that hydrogen is only produced where renewable energy would otherwise be curtailed. So this model would require an electrolyzer to handle variations in power input, and both pressurized alkaline and PEM should be able to handle this sort of varying load. And then the last one, Finlay, is looking at congestion management. So during critical peak loads of the electricity grid, large-scale electrolyzers can support this in reducing their electricity demand or potentially ceasing operation completely. Obviously, there must be economic incentive for this. However, additionally, the practicalities of the sort of end user for hydrogen needs to be considered. The flexibility of hydrogen production operation in this case would be based on the capacity of hydrogen storage, for example. And this model is quite similar to the one I've just mentioned, in that an electrolyzer would need to be able to handle the variations in the power input. Okay, thank you. Next slide, please. And back to Finlay for collocation.
Yep. So I guess to round things off, I have a quick few slides now on collocation, which essentially takes what Gwen's been talking about there and just maps how the different sections of the hydrogen value chain and some considerations we can make along the way. So during our report, we put it into 4 buckets: upstream, midstream, downstream, and hybrid. Now, not to be confused with obviously the oil and gas segments. This is related to hydrogen production with renewables. So if we take upstream, for example, we could co-locate the renewable energy source and the hydrogen production together. For example, this could be an offshore wind farm and an offshore hydrogen production platform, or it could be an offshore wind turbines with individual electrolyzers on the turbines themselves. We then have midstream, which would be when we connect the production, we co-locate the production and the storage together. So for example, we could have offshore wind power landing ashore, having hydrogen production, on-site storage, and then the end users elsewhere, so we'd have to transport it to the end user. Then we have downstream, which would be if we had the production, storage if needed, and the hydrogen end user all together. So for example, in that case, you'd have offshore wind landing to onshore hydrogen production, storage and end user in the same place. And then we can have hybrid, which could be a mixture of all 4. So it could be onshore wind, onshore hydrogen production, storage if needed, and the end user. And to maybe go into one in more detail and give some further considerations, we'll take upstream co-location. So here in the diagram above, we have electricity generation. So let's say it's an offshore wind turbine. That's going to be producing AC power, so we need to convert it into DC before we can feed it into the electrolyzer. We then have